As intriguing as space is, you don't have to go very far to find the most interesting, dynamic, and beautiful celestial object out there. It has a surface ocean of water, an oxygen-rich atmosphere, and a comparatively powerful magnetic field. It also has one very unique characteristic. It is the only place we know of that contains life, as well as it being the place we call home. And yet, even though we live here, there is still so much we have yet to learn about our own planet. So, what makes this little blip in the vastness of space so special? And what have we discovered about it so far? Let's start off by giving you some context to this planet. You may have heard that people call the Earth pear-shaped or even egg-shaped. I think this is a bit disingenuous, designed to make people think of a very odd-looking Earth. Although it is true that the Earth is not a perfect sphere. The Earth is wider at the equator than at the poles, but only by about 45 kilometers. This is because of the rotation of the planet, causing the planet to bulge at the equator. This means the furthest point from the Earth's center of mass is not the top of Everest, but rather the Chimborazo volcano in Ecuador. On average, the Earth is 12,742 kilometers in diameter. Earth has long been the talk of ancient scientists, philosophers, and others as they try to place our location in the universe we live in. Does the universe revolve around us? Do we orbit the sun? And, dare I say this on YouTube, is the world flat or round? Although the idea of a round Earth has been bandied around by Greek mathematicians since the 6th century BC, but it wasn't until Eratosthenes around 240 BC that the circumference of Earth was estimated. The method he used was quite ingenious. He heard that during the summer solstice in Syene, a city in southern Egypt, the sun was directly overhead. But in Alexandria, a city in northern Egypt, the sun still cast a shadow. Using the angles of the shadows, he was able to work out the circumference of the Earth accurately to within 5 to 10%. The 16th century brought about the heliocentric model, where we discovered, through the help of Nicolaus Copernicus, mathematical predictions by Johannes Kepler, and observations by Galileo Galilei, that the sun is the center of the solar system, not the Earth. Today, building on the legacy of these and many more brilliant people, we now know that we are the third planet from the sun and one of 4 terrestrial rocky planets. Earth orbits on average 150 million kilometers from the sun, 147 million kilometers at its closest point, and 152 million kilometers when it's furthest away. It takes 1 year to complete an orbit, rather unsurprisingly. But what is interesting is that our method of keeping time is maybe not as exact as you may think. For instance, Earth actually takes 365.25 days to orbit the sun once, which is why every 4 years we have a leap year to account for the quarter of an extra day in our year. A month is meant to match up with an orbit of the moon around the Earth, the words month and moon being closely connected. But the moon takes 27.3 days to orbit the Earth once, and our calendars don't reflect that. After all, it would be difficult to fit months that length into a 365-day year without some messy, leftover days. So those in charge of making calendars throughout history mostly didn't bother trying. And in a similar fashion to our years not being exact, our days aren't exactly 24 hours either. A sidereal day on Earth, or in other words, Earth's rotation of 360 degrees relative to fixed stars in the sky, is roughly 23 hours and 56 minutes. So where do those 4 minutes go every day? Well, the answer is that we don't actually use a sidereal day to measure our time. We use a solar day, or the point where the sun goes full circle in our sky and reaches the same place as the previous day. How is this different from a sidereal day? Well, we use a solar day because the Earth isn't stationary, and as it orbits, it moves slightly forward compared to the previous day, changing the angles relative to the sun. It needs those extra 4 minutes to have the sun lined up exactly overhead again each day, which is what gives us our exact 24-hour days. Although, it gets even more complicated than that if you really want to delve into this, as due to the Earth's slightly elliptical orbit and axial tilt, True solar days can vary by up to 30 seconds throughout the year. In order to counterbalance this, we use the mean solar days, which averages all these variations throughout the year together. Going further again, with tidal drag from the moon slowing down Earth's rotation, our days have actually become longer by about 2 milliseconds per century. This doesn't make such a difference to us, but 500 million years ago, models show that days were under 22 hours, and there were about 400 days in the year. With all this combined, keeping time is probably more complicated than you might have thought. The rotation of Earth can be beautifully observed from the ground through time lapses at night, with the fixed field of stars moving across our view. The exact axis of rotation of the planet able to be seen from the points the stars seemingly circle around. The orbit around the Sun combined with the axial tilt of the Earth means that, throughout the year, the Sun's position at the same time every day will be different. This can be seen in an anelalama, a photo of combined shots taken throughout the year. As you can see, the Sun moves in a figure of 8 shape throughout the course of the year. The north to south movement is due to the axial tilt of the Earth as it orbits, something you've no doubt noticed with the change in seasons, with the Sun being higher in the sky in summer than in winter. The variation in east to west is due to the orbital eccentricity of Earth, combined with something called the equation of time, which is, very basically, what we talked about with the variations in a sidereal day, a true solar day, and a mean solar day. This graphical representation shows the combined effects of the equations of time, the axial tilt of Earth, and its orbital eccentricity. If you were to take an anomaly on another planet, each planet's anomaly would look different. Here is a simulation of what it would look like on the other planets. Again, the differences are due to the differences in the days, orbit, and axial tilt of the planets. Earth's rotational axis is roughly 23.5 degrees to the plane of the solar system. This axial tilt is what gives is such varied seasons. Interestingly, the changes in temperature between seasons are not mainly due to the closer proximity of a point on Earth during that hemisphere's summer, but rather it is due to the amount of sunlight hitting that point. Being an extra few thousand kilometers closer to the Sun doesn't play such a large role when the distance between the Earth and the Sun is 150 million kilometers. If it did, we would find that the Earth's perihelion, or the closest Earth gets to the Sun in its orbit, would make a massive difference, because at the perihelion, we are 5 million kilometers closer to the Sun than at aphelion, or the farthest part of Earth's orbit. If you still think it does make a difference, could you take a guess at when the Earth last reached perihelion? It was actually only in January. What really makes a big difference to the temperature between seasons is the surface area the sunlight hits. During summer, when the Sun is overhead, a point will be exposed to a much more concentrated amount of sunlight. During winter, with the Sun low in the sky, the same amount of sunlight spreads out over a much larger surface area. Also, during summer, days are longer, allowing more sunlight to reach the surface compared to winter. As sunlight hits the ground or ocean, heat is released into the atmosphere. Earth has a reasonably dense and compact atmosphere, although it has a low overall mass in comparison to places like Venus and Titan. It consists of mainly 78% nitrogen, 21% oxygen, and 1% argon, with trace amounts of other gases like carbon dioxide. Water vapor is also present in the atmosphere. It can vary wildly from only 0.01% to 4%. But it averages out at 1%. It's this water vapor that makes clouds in the atmosphere. O3 is also present in a special layer in the atmosphere called the ozone layer. This ozone absorbs a lot of the harmful ultraviolet radiation from the Sun, which protects life on land and allows it to flourish. Without it, Earth would be a dangerous place to go outside for life forms like us. The atmosphere, in fact, serves the life in many different ways. It provides useful gases like oxygen and CO2, causes small meteors to burn up before striking the surface, and even moderates temperatures around the globe. With the atmosphere retaining some of the heat from the Sun, the Earth would be a far chillier place, minus 18 degrees Celsius on average compared to the actual 15 degrees Celsius average now. The atmosphere also drives one of the most essential systems to us, the water cycle. As the sun warms the Earth and its oceans, water on the surface evaporates and rises. This water vapor later cools and condenses on dust particles in the air to form clouds. In this form, the water particles can travel considerable distances before eventually falling in the form of rain. The water is then transported back to the oceans through rivers, which completes the cycle. Not only does the traveling water erode the surface, it is also vital to the life that lives on the surface. From plants to bacteria to animals, all need water to live. Another hugely important system on Earth that I've mentioned already is the Earth's hydrosphere, predominantly its oceans. The prevalence of life on land is hugely reliant on the oceans of Earth. The oceans on Earth are vast, making up 1/4,400th of Earth's total mass. To give you a sense of scale of the Earth's oceans, if the Earth's surface was completely smooth, the entire planet would be covered in an ocean almost 3 kilometers deep. Luckily for us, that is not the case, and the Earth's surface is highly variable. This is due in part to quite a unique feature of Earth, its plate tectonics. You see, Earth has a comparatively thin crust, underneath which is a hot and active mantle. We sometimes see the effects of this mantle flowing underneath us as the plates on the crust bump, scrape, and pull apart from one another, forming volcanoes, earthquakes, mountains, and trenches. Using an exaggerated 3D map of the elevation of Earth, you can see clearly mountain ranges and deep trenches that are formed thanks to plate tectonics. As a result of this, you may think that plate tectonics are dangerous to life on Earth, and perhaps to individuals in the wrong place at the wrong time. It could be. But this renewal of the surface keeps the Earth fertile and fresh. Underneath the mantle is the planet's core, consisting of primarily iron and nickel. Earth is the densest planet in the solar system at 5.5 grams per centimeter cube, and this is mainly due to the core. It is very big compared to other planets, the outer core reaching roughly 5,000 kilometers in diameter. The inner core is thought to be solid, but also has extreme pressures of 360 gigapascals. It reaches 6,000 degrees Celsius in temperature. The core is also where the magnetic field of Earth originates. As the core moves, it converts kinetic energy into electrical energy, generating a massive magnetic field around the planet, kind of like the magnetic field around a giant dipole magnet. This magnetic field also serves life on the ground, as it diverts solar winds, or highly energized particles from the sun, around the planet and also to its poles. Without this, solar storms would regularly bathe the Earth in deadly charged particles, which would destroy our DNA and strip away our atmosphere. But with it, we are lucky enough to see beautiful aurora, where the particles interact with the atmosphere. The most common color for auroras on Earth is green due to the solar wind's interaction with atomic oxygen. There's one more very unique aspect about Earth that I want to cover in this video, and that is its moon, known as Luna. Although many other planets have moons, Earth has the largest moon relative to the size of the planet. The result of this is a spectacular sight in our sky on a clear night. A huge celestial object that is so close that we can make out details on its surface with our naked eye. But having something so massive, so close to us, has a very real effect on our planet too. The moon influences our ocean tides through its own gravity, which pulls at the water in our oceans, causing a bulge as the planet rotates. This bulge even exists in the Earth's crust, although to a less noticeable degree. However, these tidal forces could be the reason Earth has such active plate tectonics. Having done all the research for this video, it kind of blows my mind to think how many factors had to be right for life to have formed and developed on Earth. But as a result of all these factors aligning, we are now a part of a species with a population of more than 8 billion people. A species with the intelligence to question our own existence and to find our place in this universe of ours. It also amazes me to see the beauty of this planet. Thanks to space exploration, we get a view of our home that people would have only dreamed of 100 years ago. Will anything else in space ever be as beautiful and welcoming as this, our home planet? Let me know what you think in the comments below. But for now, thanks for watching.